Looks like it's about that time. I'll get started. My name is Erik Taubeneck. This is Hack the Derivative. I'm a software engineer at a company called Game Changer Media. We're in New York, but I grew up in Seattle, so I'm really happy to be able to come back and present here. We're hiring, so if anybody is interested, you can check out that link. So let's get started. So just quick outline before we dive right into it of sort of what I'm going to cover. We're just going to start with like a real quick calculus crash course in case you don't remember, that Calc 1 course back in college about exactly what the derivative is. Then we're going to talk about the finite difference method for estimating the derivative and going to break it. And to figure out why it breaks, we're going to look at floating point arithmetic and the implementation of floating point numbers. And then we're going to try and do better, but before we do that, we need to understand a little complex analysis and use some imaginary numbers. And then once we've got that sort of under our belt, we're going to hack the derivative. If anybody feels like they want to follow along or check it out afterwards, there's like 6 functions that I use, so I put them all in a Python file and you can pip install it. It's also on GitHub. So if you feel like using these functions, you don't have to copy them on the slides. They're all pip installable. So taking the derivative. So we're going to consider a function f of x, and it's going to map from r onto r. It may not map onto all of r. So for example, our first one here, x squared, the result of that's always going to be positive, so it's going to map onto a subset of R. Our last example here is not actually defined at x0, so it's actually mapped from a subset of R to a subset of R. But all of these, we have all these functions we can take the derivative of. Now the derivative, if we look at sort of a graph of the function, the derivative is the slope at any given point. And so to see that, we sort of like draw a tangent line that only touches the graph at a single point, and the slope of that tangent line is the derivative at that point. So unless your function is linear, that slope changes as you move around the function, so those tangent lines change. And so the derivative gives you a nice way to see what that slope is at any point. So a little more formally, if we want to take the derivative, it's the limit as h goes to 0 of f of x plus h minus f of x over h. So essentially, if we go back and look at this, we're taking 2 points from the function, drawing a line between them, and looking at that slope, and then we're taking the limit as those points basically become the same point. This limit needs to exist from both sides in order for the derivative to exist. So for example, we're going to look at x squared. We're going to use x squared quite a bit through this presentation. Just plugging into the definition of the derivative, we have f prime equal to this. And if you remember your FOIL operations, you can expand that out. And now those x squareds subtract from each other. And now we can factor an h out, and we get 2x plus h. And the limit of as that goes to 0 is a pretty simple problem, and we just get 2x, and we have the derivative of x squared. So now suppose we have some function that we want to find the derivative of at some particular value. We're going to call it x naught. And we don't necessarily want to do it with pen and paper. We want to do it in a computer. So one approximation that we can do is called the finite difference method. So that we have this same definition. And to estimate it, we can basically just plug in an h that's really small. And that's going to be pretty close. So we can implement that in Python very easily. We just plug right in. And so here's our x squared function, and we can find the derivative at 1, and we plug in some small value for h, and that's pretty good. That's pretty close. So now we have to figure out, well, how do we choose the h? we really want the limit as h approaches 0, so probably the smaller the better. So if we like hop in and we can actually get the smallest float that Python can handle, and we set that equal to h and plug that in, oh crap, that doesn't work. So, well, the one with the 4 zeros in front of it seemed to work pretty well. Maybe it'll just work. But sure enough, that will break too. So if we try and take the derivative at some very large number and use that, we're going to get 0 too, and that's not the right answer. So in order to figure out sort of what's going on here and how that's failing, we're going to take a closer look at the floating point numbers. So this is the basic implementation of a float 64. A float 32 is very similar, but obviously not as much precision or as many exponent bits. But we're just going to look at 64. So that has one sign bit, so that tells you if the number is positive or negative. 11 exponent bits, so that is basically scaling the floating point number so that you can get very small or very large numbers. And then 52 bits, which are the fraction. And so the way that that's implemented, you can look at either of these two formulas. In the top one, the b's there are binary, so it's just going to be 1.0101. That's all base 2, and then you get 2 times whatever the exponent is, and so the exponent ranges from negative 1023 to positive 1023. So you can basically think about this, now it's not exactly, but as a big integer, 52-bit integer, and then some exponent that sort of tells you like where that scales to. And so because of this, you have like a fixed amount of accuracy. And that means that there are gaps between the floating point numbers. This isn't true about the real numbers. And so the real key here is that the gaps change. And so this image sort of demonstrates that nicely. The gaps near 0 are quite small because you have a lot of accuracy there. As you get to very large numbers, those gaps are bigger because the accuracy is relative to like where you're at in the real numbers. And so this leads to situations where you can essentially take one floating point number and add it to another floating point number and not go anywhere. You'll essentially round off. And so I've written this little fun function called plus epsilon identity, which just basically says give me an x and some small value, and we're going to add them together and see if we actually go anywhere or not. So if we set it back equal to this, this smallest float that we have in Python, or really in any floating point implementation, if we're at 0 and we add that to it, we do go somewhere. It's not the same thing. But however, if we're at 1 and we try and add that to it, we're not going anywhere. And so if we get to some really big numbers, actually, we can add a whole integer to it, like 1 to it, and we really don't go anywhere. So the gaps really do get quite big, and this can lead to some problems. So the essential problem here is, given wherever we're at, where we're taking the derivative, if we choose an h that's too small so that we don't really go anywhere, well, if we plug that into the definition that we have for the derivative, f of x plus h is really just f of x again, and we subtract those, we get 0, the derivative ends up being 0, and we don't go anywhere, and that's not very fun. It's obviously going to lead to wrong answers, unless you happen to be at a place where the derivative is 0, and it just kind of magically right on accident. So to sort of figure this out, we can write a function that will find us sort of what the base epsilon is at any given x. So this basically just plugs in an epsilon and then just doubles it until you actually go somewhere, and that gives you a very close estimate, so sort of how big the gaps are at the x value that you're looking at. So we can plug that in. We can see, okay, so what's the gaps at like 1.0, and it's 16 or 15 zeros and a 2, or point and then 15 zeros and a 2. And then if we go up to a 1 with 10 zeros, we have 6 zeros and a 1. So still pretty small gaps for quite a ways, but it does you can see as we go up an order of 10, we lose an order of 10 in the size of our gaps. And so if we go up even really big to like 1 to the 20, which is where we saw it fail earlier, the gaps are like over 1,000, which is pretty big. And so that is basically what's causing our problems when we take the derivative. And so I found these lecture notes online. I'm actually curious why I wasn't able to find any other research around this, but there was a really great proof basically using a Taylor series to estimate the error that you get from the floating points compared to the error you get from using the finite difference method, and they suggest using an h that's around this value where you take basically the square root of x at 1 and then multiply it by either the absolute value of x or 1. You can check that out. The math seems solid. So if we implement that in our finite difference method, we can now basically just not pass an h into this function and it will compute it for you. So we can test that out. So to test that out, I've written a couple more functions. One just tells me, hey, what's the error? So to test this out, we obviously have to have the function, and we need to know what the derivative is. So we just plug those in and subtract them, and that's the error. And then we can divide that by what the derivative actually is to get sort of an error rate. And so if we plug in, we're going to use x squared again. We know the derivative is 2x. So we get some error rates they're small. They're not 0, but they're, that's reasonable. So what happens if we look at like sine and cosine? So we know that cosine is the derivative of sine, if you remember back from Calc 1. And so, at 1, we get a pretty reasonable error rate, but at 1 with 10 zeros, 1 with 20 zeros, there's a pretty bad error rate. This is about as bad as it gets for sine and cosine. So that's not good, and we can do better. But we're going to have to use some math. This is where it gets fun. So we're going to have to use some complex analysis. How many people in here have seen this before? I equals, square root of -1. Okay, so good. So, if you haven't, you may wonder, well, why do we need this funny thing? So if someone, tells you, hey, go and solve this equation, x squared plus 1 equals 0. If you're limited to the real numbers, you're not going to find a solution. For the real numbers, x squared is going to be either equal to 0 or greater than 0. And if once you add 1 to it, it's always going to be greater than that 0. You're not going to find a solution. But you plug in I and you square it, you get -1, that equals 0. So we define this whole new set of numbers called the complex numbers, where it's basically just two real numbers, but you add them together, it's x plus iy. And so this basically allows you, for any polynomial, you'll be able to find, for an n-degree polynomial, you'll be able to find all n zeros. So that's pretty fun. So we're going to work through an example. So now we've got f of z is z squared. And so we're going to rewrite z as x plus iy. And so if we plug that in and carry it all the way through, we can expand that, and we end up getting the I squared becomes negative. We get x squared plus 2i xy minus y squared. And so given any complex function, you can always separate it into its real and imaginary parts of the function. And so those are usually written as u of xy and v of xy. And so the u of xy is the real part, v of xy is the imaginary part. And so in our example, u of xy is just x squared minus y squared, and v of xy is 2xy. Note that the I is not in the v. It's when you define the function, it's I times v. So there's both of these functions are actually real valued functions. So now we have this function sort of written as these two functions, and there's 4 derivatives that you can take, because we have 2 functions and each one with 2 variables, so we can take a partial against both of them. And so if we take each of these partials, we get 2x, 2y, negative 2y, 2x. And there's a nice little pattern there, sort of going diagonally. du dx equals dv dy, and du dy equals negative dv dx. And so these are the Cauchy-Riemann equations, and they hold for all analytic functions in C. You can go check your favorite complex analysis book for a proof if you want. I'm going to leave it to you guys for now. Unfortunately, don't have time to go through that. But this is going to come in pretty handy. So it's time to do the hack. So we have a function from R to R, and we're going to rewrite it. And so now, because we are taking this function from R to R, we can consider z bar to be some element that's just in R. And so since it's in R, if we write it as x plus iy, the y part is going to be 0. Because it's a real number, so x plus iy, if it's real, y has to be 0. So we can now rewrite f of z bar equals f of x 0. And then we can separate that into the two functions, just like above. And we have u of x0 and I times v of x0. Additionally, since we're mapping onto R, we know that the v part is going to be 0. And so we get f of x0 equals u of x0. We're trying to take the derivative of f with respect to x, and for all of the z's that are part of R, we know that f equals u, and so the derivative of f with respect to x is going to be equal to the derivative of u with respect to x, which we know from the Cauchy-Riemann equations is going to be equal to the derivative of v with respect to y. And so if we go back all the way to the beginning to the definition of the derivative and take dv with respect to y, we can just plug this in here, v of x y plus h minus v of x y over h. And then we know that y is 0 because we're taking a z that's in R, and so we can just plug in y equals 0 here. So we get v of x h minus v of x 0 over h. We also know that v of x 0 is 0, so we just get v of x h over h. And so to estimate the derivative, we can just take the function evaluated at x plus ih and divide by h. And so the magic that we've sort of done here is we've taken something that normally takes subtraction, which is a very difficult operation for floating point numbers to do, and eliminated that subtraction and made it just like a straightforward evaluation of a function at a single point, and then a division. Now, if you think about the floating point numbers, it's very difficult to do addition because if two floating point numbers are of very different accuracy, you're going to get a round off error, you're not going to go anywhere, like we showed with that epsilon problem. But with division, because of commutativity, we can divide the two digits that are of accuracy separately than the exponents. And so we don't lose any accuracy in the division. And so we end up getting far more accurate results. So to implement this in Python, in Python and actually in most programming languages, the imaginary unit is represented as a j rather than an I. And that's because I is typically used for counting and things like that, so you don't want to conflict with that or override it on accident. So we just we can take this min float now and just use it, and then we can take that step in the imaginary direction. And so if we do that and we get our original functions again, and we plug that in, 2.0, and 2 with the right amount of zeros, and 2 again with the right amount of zeros. So those are exactly right. If you don't believe me, we can define these error functions again, and if we go through, we have an error rate of it perfectly 0. So this is pretty awesome. So what if we what if we check it out on the sine and cosine? So the one trick here is that we have to, Python has a C math package that allows for complex implementations of functions like sine, cosine, the exponential function, square root, things like that. We need functions that take complex numbers. So sine and cosine, 0.0, 0.0, 0.0. Now, this is pretty good, but it's not perfect. We can find, so this is, again, for sine and cosine. If we take one with 5 zeros, we get a little bit of an error. Here's a more complicated derivative function. I just Googled like fun derivative problem. So this is exp of x over square root of x. And this, I plugged this into Wolfram Alpha to make sure that I did the math correctly for the derivative. And so that came out. So that one at 1.0, you get no error, but at 10, you get a little bit of an error. At like 5.67, I threw something in there, you get a little bit of an error. If you go up to just 100, or rather 1,000, you get an overflow error. And so the C math, I think it's the X function, doesn't work very well for even relatively small errors. So this does have some pretty stark limitations around like what can be computed. That doesn't mean that you couldn't write a better complex implementation of X to get this to work. So a few more limits. The function obviously has to satisfy the Cauchy-Riemann equations. So if you have a function with like absolute value, this isn't going to work. If you have a function with like some logic flow in it that uses like a less than or greater than in it, it's not going to work. And obviously, all the assumptions that we made to cancel out and use the Cauchy-Riemann equations assumes that the function is going from R to R. And so if we want to find the derivative of a complex function at a complex value, this isn't an appropriate solution. This leads to some interesting questions, though. These are some fairly trivial examples, absolute value, less than, greater than. But for a great majority of functions, so if you have an implementation of the complex numbers, it's actually pretty difficult. Aside from building a function where you just throw abs in there, to find a function that this isn't going to work on, that sort of gets into some mathematical philosophy about the nature of functions and whatnot. But by the way that we're able to sort of codify functions, we are lucky enough to usually have this condition met. So that's all I got. I've got plenty of time for questions. You can check me out online. I've got these slides up online. Yeah, thanks. Yeah.
It's been some time that I've done PDs, but what's the difference between just using spectral methods versus doing this?
So I'm not familiar with the spectral methods.
So basically take the Fourier transform.
Oh, sure. That's a good question. So,
It generalizes for a number of years.
sure. So if you're using a Fourier transform, I believe you would have a complex valued function, and so.
No, if you convert it, you go back to the whatever.
Sure. So the Fourier transform is basically going to extract the frequencies out of a signal. So this is slightly different, and you're trying to find like the actual point derivative at a value. Maybe if you worked out the math, this may actually be going on in the background. I'm not. So no, this isn't. This is something that I worked on 2 summers ago. Actually, in Julia, there's a calculus package, and I was in hacker school at the time, and worked with a couple Julia contributors on their calculus package, and discovered this and was pretty amazed by it. And so I've been sort of researching a little bit more and putting slides together to talk about it and whatnot. Unfortunately, I don't have a lot of opportunities to take the derivative of arbitrary functions at work, but would be fun. Any other questions? Yeah.
To answer your pseudo-spectral method question, usually that's if you have a function defined at different points. And this is if you already have a definition of the function that you can evaluate. So once you have a bunch of sample points, you're essentially using Fourier transforms to fit a curve through it, then compute the derivative using information not just at that one sample point, but for all the samples. And that's a completely different question, what this is trying to answer. This, you already have a function that you can evaluate at arbitrary precision to then compute the derivative.
I disagree, but I think we can.
Any other questions? We got plenty of time. All right, thanks.